Every year, gamblers lose over $100 billion to casino and online betting sites. The house always wins. But what if AI could change that? So first, we're going to need to get our hands on a lot of data, and I've gone ahead and done that. In this data set, we have the game, the gender, age, bet size, time of day of the week, loyalty level, session length, drinks consumed, previous wins, and then whether they won or not. And here's exactly how we're going to do it so you can do it as well. We're going to be using AI and machine learning, a model called random forests. Random forests are made up of a bunch of decision trees. Think of it like asking a series of yes or no questions, each to reach an answer. It's simple, but it can get wrong. So what we do is we put a bunch of these trees together, and instead of relying on just one, the random forest takes multiple trees and aggregates or combines that answer, taking the average. So a single decision tree might look at one feature like age. Was the player 20 or older? Yes. Well, did they win? No. So maybe I've decided being under 20 gives me a higher chance of winning. But again, that can be misleading. So lots of trees look at lots of different areas and analyze these factors and come up with the best ways to win. And we've put that here to the test. And this is the actual random forest that we generated today using AI. Yeah, it's a lot. So here's the code. It's inside Jupyter Notebook. It's a lot of machine learning in Python. And if you want to learn how to do all of this, then head over to my website at tobygeeson.com. If we go over to the shop, you'll find a bunch of different notebooks that have helped over 70,000 learners land their data science dream jobs here. All your lovely comments here, so I appreciate that a lot. Now, if we pick one of these, like machine learning, you can see you'll get a full pack, exactly step by step, taking you along the machine learning journey from beginner to expert. Now, let's get into it. So once we've created this model, we can then explore it, and here's exactly what I found. We can see that the average age was 48, with the oldest player being 79 and the youngest being 18. People on average stayed for 92 minutes and had won previously about 10 times. The most previous wins was 19, with some people having never won before. This gives us a good picture of the dataset before we get into anything further. Again, here we have the feature importance, showing that session length in minutes is the most important feature, suggesting how long you play really does have an impact. And so does age. And as you may expect, previous wins, both sorts suggesting experience. Gender is the least important. Looking at the win distribution, we can see that the majority of people don't win. That's class 0. Whereas people do win, just less often. Now, looking at this pair plot, it's a very big chart with a lot going on. It shows the relationships between all the numerical features in the dataset. And here there doesn't seem to be any that are particularly strong, but we can examine that with the correlation matrix. Next, we have the correlation heat map. We can see that most variables have very weak correlations with one another, meaning they don't strongly influence each other. For instance, win has weak negative correlations with most of the other variables. We ran a box plot. The summary here indicates that the numerical features in the dataset do show variability and may contain outliers. This is helpful to identify the range, distribution, and any potential anomalies in the dataset. So it shows the two classes 0 and 1, 1 being when they won and 0 being when they lost. If we look in the bottom left, we can see previous wins by wins and losses. On average, the middle line or the median is higher for no win, 0. Than it is for 1. This is also the case in drinks consumed, whereas in the other plots, it's fairly similar. The bet size by win and losses, we can see the boxes are quite small, indicating that the interquartile range, or IQR, which is the range between the first and third quartiles, is small. This means the middle 50% of the data is tightly clustered, indicating a low variability or dispersion in that range. Now, the dots outside of the whiskers are outliers. These are data points that lie significantly outside of the expected range, and we can see these as unusual observations. Equally, we can look at the line length. These are the whiskers. Now, long lines represent the range of the data. Longer whiskers suggest that there is greater spread or variability. We can actually see here the best conditions to win are as follows. Be 48 years old, bet 240, you want to have a loyalty level of 2.4, a session length of 91 minutes, and have about 9 previous wins. Then we have the confusion matrix. We can see true negatives, 501, are correctly classified, but there are 117 false positives, indicating that the model sometimes incorrectly classifies negative instances as positives. False negatives, bottom left, 296, and true positives, 86, indicate that the model is missing a significant number of positive cases, which is reflected in the low recall for class 1. So precision here is how many of the instances predicted as positive were actually positive. It tells you the accuracy of the positive predictions. You can see class 0 has a higher precision, 0.63, than class 1 with 0.42, meaning that when the model predicts class 0, it's more likely to be correct. However, for class 1, the model is less reliable. In a way, it's more likely to make false positive predictions. Now, recall measures how many of the actual positive instances were identified correctly by the model. It tells you the model's ability to find out all relevant positive instances. So class 0 has a higher recall at 0.81 than class 1 with 0.23, meaning the model is good at identifying negative instances, but it can struggle with positive ones, meaning it misses a lot of them, only correctly identifying 23% of actual positives, which brings us on to the F1 score. This is the harmonic mean of precision and recall, providing a single metric that balances both concerns. It's especially useful when you need to balance the trade-off between precision and recall. Here, class 0 again has a higher F1 score than class 1, meaning the model is more balanced in its ability to both correctly identify and avoid false positives and false negatives for class 0. Class 1 is a lot lower, meaning the model is not performing well with the positive class. And then you have support, which refers to the number of instances of each class in the dataset. It's simply the count of samples for each class. We can see that class 0 has more instances, so the model has more data to learn from, which actually gives us some context as to why it may be performing better. Every year, gamblers lose over $100 billion to casino and online betting sites. The house always wins.